This is your warm-up problem. Press pause, and when you're ready to see the answer, press play again. Here's the solution. You were supposed to solve it with an identity. I used 1 minus 2 sine squared theta for cosine of 2 theta. And then I solved for sine squared. I took the square root of both sides. And remember, when you take the square root of both sides, it's either positive or negative. And then I found that my reference angle was 15 degrees. Since my answer could be either positive or negative, I knew that I was going to have an answer in each of the 4 quadrants. So I had, again, 4 answers, each with reference angle 15. So my first quadrant, my angle was 15. And my second quadrant was 180 minus 15, or 165. I don't know why that, I'll write that better on there. 165. It looks a little bit better. And the next angle in the third quadrant is 180 plus 15, or 195. And then in the fourth quadrant, it's 360 minus 15, or 345. Now, today what we're going to do is we're going to solve this kind of problem in a slightly different way. So, here's another way to solve it. Same exact equation, but this time I'm realizing that I know that an angle whose cosine is square root of 3 over 2. And that angle is 30 degrees. So, I know that 2 theta is 30 degrees. I also know that that's my reference angle. So, cosine is positive here, and I know I'm going to have an answer in both the first and the fourth quadrants. Same reference angle, 30 degrees, 30 degrees. So 2 theta can be 30, or it can be 330 degrees. Remember, 360 minus 30. Now, the thing is that theta can be between 0 and 360, but 2 theta can be between 0 and 270. So what I need to do is, to each of these, I need to add 360 until I am outside of my constraint. So I added 360 to each of those. And if I were to add 360 again to either of these, I would be higher than 720. Now, at that point, I solve each of these for theta by dividing by 2. So I have 15 degrees, 165, 390, and 690. And you can tell that those are the exact same answers that I got using an identity. Now, that it works, just so happens that it works 2 ways for this kind of problem, but if I'm dealing with a triple angle or a quadruple angle, not so much. This would be the only approach you could use. So, what I want you to do is I want you to solve this problem where x is between 0 and 2 pi. Press pause, and when you're ready to check your answer, press play again. Here's the answer. I knew that tangent was 1 at pi over 4. That's my reference angle. So I knew that 3x was either pi over 4 or 5 pi over 4, because tangent's positive, and it's positive in the first quadrant and also in the fourth quadrant. So this angle I got by taking pi plus pi over 4. Then I needed to add 2 pi to each of these, because remember, x is between 0 and 2 pi, but 3x is between 0 and 6 pi. So I added 2 pi to each of those and got these values. And then I did it again and got these values. And if I were to add 2 pi again, I would be outside the constraint. So at that point, I'm done. Then I take each of these and I solve for x by dividing by 3. Now, I can also solve equations just like this, only that I want all solutions this time, rather than just between 0 and 2 pi. And it actually, when you start getting into these higher angles, it's actually easier to do. So make sure you have this written down before we start talking about it. Okay, so you begin solving this exactly the same way as I did the last one. I still know my reference angle is pi over 4. I know that I have another answer in the third quadrant. 5 pi over 4 over here and over here, and those are exactly pi apart. So since they're exactly pi apart, I can write one equation to represent both of those two. It is pi over 4 plus k pi. Because every single time I go around, I hit another answer. Every time I go around pi. So at that point, what I do is I divide everything through by 3. I divide pi over 4 by 3. That's where I got the pi over 12. Divide k pi by 3. That's k pi over 3. Now remember, k is an integer. We have to agree that k is an integer, otherwise this will not work. So, also in this particular case, we were exactly pi apart, so I could add pi. Sometimes that's not the case, but I can also represent this in a slightly different way. I could then say 3x equals pi over 4 plus 2k pi, and I also could say 3x equals 5 pi over 4 plus 2k pi. So those would be both of my answers between 0 and 2 pi, and again, I could divide both sides by 3.
I'm sitting.
Now, even though these answers look different, they will still produce all of the exact same answers. I prefer this one because it's more concise, but I would accept this answer as well. And I don't know why I wrote a 4 there. That should be a 12. Okay, so I would accept either of those answers as correct. Now, this one is similar, but it's a little bit different in that I have to factor it first. So why don't you give this one a try? When you're ready to see the answer, let's play. Here's the solution. You'll notice that I factored. And then, did I find all solutions? Yes, I found all solutions. So I knew that my reference angle here was pi over 4. Really, to find the reference angle, remember, I take the inverse sign of the positive, which is very nice, but in my calculator, I could do it in my calculator, but I know very well that the reference angle is pi over 6. Okay, so I have an answer in the third quadrant and in the fourth quadrant since sign is negative. So my first answer is pi plus pi over 6, or 7 pi over 6. My second answer would be 2 pi minus pi over 6, or 11 pi over 6. Now, I want to know all solutions. So every single time I have an angle here or here, I'm going to get another answer. So to each of these, I have to add 2k pi and then solve for theta. So dividing both sides by 3, I get 7 pi over 18 plus 2k pi over 3. Over here, 11 pi over 18 plus 2k pi over 3. There is no other shorter way to write this, as was the case of tangent, because these are not at regular intervals apart. Okay, now we're going to do this problem. It's a little bit different again. We don't know any identities for sine of x minus cosine of x. So we're going to have to change things around a little bit in order to solve that. So in order to solve it, I need to square both sides of my equation. So once I square both sides, I notice that I have a sine squared x and a cosine squared x right here and right here. And those added together are 1. So I replace that with a 1, and I have 1 minus 2 sine x cosine of x equals 1. Solving for that, I subtracted 1 from both sides. And then I noticed that this is really sine of 2x. I don't know why I didn't divide by -1, but for whatever reason, I chose not to. But in the end, it's okay because I end up with sine 2x equals 0. And that happens. Hold on, something's weird with my pen. Oh, here we go. So that ends up telling me that I have the terminal side of my angle on the x-axis. Sine is 0 when y is 0. So I know that 2x equals 0 or 2x plus 1 or 2x equals 180. So I have to solve each of those for x. Now, notice that x was between 0 and 360, but 2x is between 0 and 720. So to each of these, I have to add another 360 degrees. So that will also be true when I hit 360 and when I hit 540. Again, I divide all of these by 2, and I end up with x equals 0, x equals 90, x equals 180, and x equals 270. However, when you square both sides of an equation, you can end up with some extraneous solutions. You have to go back and double check in the original equation if it works. So if I were to check x equals 0, I'd have sine of 0 minus cosine of 0. Well, sine of 0 is 0, cosine of 0 is 1, and negative 1 is not equal to positive 1, so that is extraneous. It does work with 90. Sine of 90 minus cosine of 90. Sine of 90 is 1, cosine of 90 is 0. So that works. If I put in 180 minus cosine of 180, sine of 180 is 0, cosine of 180 is negative 1. That one works. If we put in 270, check that. Sine of 270 is negative 1. Cosine of 270 is 0. That's negative 1. That is extraneous. So we have 2 solutions. Okay, I would like you to take a look and see what the assignment is online. And the answers are online, and you check your work as you go. Have a nice day.